Many of the pumps used to keep liquids flowing through plant piping are positive displacement pumps. They use different types of internal components to push or positively displace controlled amounts of liquid through the pump. One type of positive displacement pump that's commonly used in industrial plants is a rotary pump. Rotary pumps use the rotating motion of components like screws, gears, and vanes to move process liquid. Since rotary pumps are common to many industrial applications, it's important for operators to understand how they work. Like other types of positive displacement pumps, rotary pumps are commonly named according to the type of component that moves liquid. For example, some rotary pumps are called screw pumps because they use screw-like components to move liquid. This is one type of screw pump called a single screw or progressive cavity pump. It contains a single screw that's located inside a casing. This end of the screw is normally connected to a driver. As the pump operates, process liquid is drawn into the pump through the suction port. As the screw rotates, cavities form between the casing and the screw. These cavities move or progress toward the discharge of the pump, carrying the process liquid along. When the liquid reaches the discharge, it's forced out of the pump. Progressive cavity pumps have a few unique characteristics. For example, they can move extremely viscous liquids, like sludges and gels, without clogging. Now, not all screw pumps use a single internal screw. This is a two-screw pump. One of the screws is attached to a shaft that's coupled to the pump's driver. This screw is known as the power or driver screw. The other screw is often referred to as the idler screw. In this pump, power is transmitted from the driver screw to the idler screw through a set of timing gears. During operation, process liquid enters the suction of the pump and is directed toward both ends of the casing. As the screws rotate, the liquid becomes trapped between the casing and the screws. The liquid is moved from both ends of the pump toward the center, which is also the discharge of the pump. The force that's exerted by the screws pushes the liquid out of the pump and through the discharge piping. Now that we've seen how a couple of screw pumps work, let's stop so you can check your understanding. Select the arrow to the suction on this screw pump. Many rotary pumps use gears or lobes to move process liquid. Like other rotary pumps, gear pumps and lobe pumps can be used to move viscous liquids, such as heavy fuel oils and tars. Let's look at gear pumps first. One of the more common types of gear pumps is an external gear pump. The external gear pump shown in this illustration consists of a casing with a suction port, a discharge port, and two gears located inside the casing. One gear is rotated by the pump's driver. This gear is often referred to as a power or driver gear. The other gear moves because its teeth are meshed with the teeth of the driver gear. It's called the idler gear. During operation, liquid enters the pump through the suction port. As the gears turn, the liquid is trapped in the spaces between the casing and the gear teeth and moved along the casing. When it reaches the discharge port, it's forced out of the pump. On this type of pump, each space between the gear teeth positively displaces a given amount of liquid. So on each revolution that the gears make, a specific amount of liquid is pumped. Can the pump shown here be described as being a gear pump? This is an internal gear pump. This pump has a casing with a suction port and a discharge port. Inside the casing are a crescent-shaped spacer and two gears. The spacer prevents liquid from flowing from the discharge back to the suction of the pump. On this pump, the outside gear is rotated by the pump's driver, so it's the power or driver gear. The inside gear moves because its teeth are meshed with the teeth of the driver gear, so it's the idler gear. But keep in mind that on some internal gear pumps, the inside gear is the driver and the outside gear is the idler. When this pump operates, there are two separate liquid flow paths inside the pump. One flow path is in the spaces between the inside gear and the crescent-shaped spacer. The second flow path is in the spaces between the outside gear, the spacer, and the casing. During operation, Liquid is drawn through the suction and into the spaces formed as the gears unmesh. As the gears continue to rotate, the liquid moves into the spaces between the inside gear and the spacer. These liquid-filled spaces move with the inside gear until they reach the discharge of the pump. There, the liquid is forced out of the spaces as the inside and outside gears mesh together. The liquid that flows in the other flow path is drawn in from the suction of the pump and into the spaces formed by the unmeshing of the two gears. As the outside gear rotates, some of the liquid is trapped in the spaces formed between the gear teeth, the spacer, and the casing. These liquid-filled spaces move with the outside gear until they reach the discharge of the pump. There, the liquid is forced out of the spaces as the inside and outside gears mesh together. Another type of rotary pump that moves liquid by trapping it in spaces and forcing it out of the pump is a lobe pump. Lobe pumps use lobes instead of gears to move process liquids. The pump shown here is often called a two-lobe pump because each rotor has two lobes. But lobe pumps can have as many as 3 or 4 lobes on each rotor, depending on their design. The lobes are made so that they rotate closely together. This forms a seal between them that prevents leakage of liquid back to the suction. During operation, the lobes rotate and draw in process liquid through the suction of the pump. As the lobes unmesh, gaps are formed. Liquid is drawn into these gaps and is then trapped in the spaces between the lobes and the casing. As the lobes continue to rotate, the liquid is moved along to the discharge of the pump, where it's forced out of the pump and into the discharge piping. Now is a good time to stop and check your understanding of gear pumps and lobe pumps. Based on what we've covered, where would you say the suction side of this gear pump is located? Vane pumps operate a lot like other types of rotary pumps. They trap process liquid in spaces and force it out of the pump. There are 2 common types of vane pumps: sliding vane pumps and flexible vane pumps. This is an illustration of a sliding vane pump. This is the pump's rotor. It contains the vanes which can slide in and out of the rotor. As the vanes pass the pump's suction, centrifugal force causes them to slide outward. When this happens, the vanes trap liquid in spaces along the casing. The centrifugal force keeps the vanes extended against the casing, so the trapped process liquid is moved toward the discharge of the pump. At the discharge, the gap between the rotor and the casing becomes very narrow. This directs the process liquid out of the pump and forces the vanes back into the rotor. The reason the gap between the rotor and the casing narrows is because the rotor is offset. It's positioned away from the center of the casing, so that the gap between the rotor and the casing is very narrow where the vanes rotate back to the suction of the pump. In addition to directing most of the liquid out of the pump, this narrowing allows only a small amount of liquid to return to the suction of the pump. Another type of vane pump is called a flexible vane pump. Like other types of rotary pumps, flexible vane pumps trap process liquid in spaces and move it through the pump. In this illustration of a flexible vane pump, we can see all of the basic parts. Inside the casing is the rotor, and attached to the rotor are the flexible vanes. As with the sliding vane pump, the rotor in the flexible vane pump is offset from the center of the cavity that it's in. When the pump operates, process liquid is drawn in from the suction of the pump and trapped between the moving vanes and the casing. The liquid-filled spaces are moved along until they reach the discharge of the pump. At the discharge, the rotor is closer to the casing, so the pumping area is narrower. As a result, the vanes flex by bending over into the spaces containing the process liquid. This makes the spaces smaller and forces the liquid out of the pump. The big advantage of using a flexible vane pump is that the vanes form a tight seal with the casing. This characteristic is often used in pumps that are required to draw a vacuum on a process. In some pumping applications, it's critical to keep the process liquid away from the pump's moving parts. One type of rotary pump that can be used in these applications is a tubing pump. In a tubing pump, the process liquid is contained inside a flexible tube that's part of the pump. The pump's rotor works with the tubing to force the liquid through the pump. We can get a better idea of how this type of pump works by using this illustration. On this pump, the casing is in the shape of a U. Inside, the tubing follows the casing's U shape. Also inside the casing is a series of rollers mounted on a rotor. The rotor is attached to the pump's driver. During operation, liquid is drawn into the tubing at the suction of the pump. The rollers turn with the rotor and compress the tubing, trapping liquid inside. As the rotor continues to turn, the rollers force the trapped liquid through the tubing and out the pump's discharge. Tubing pumps normally don't have as high a flow rate as other types of rotary pumps, but they still have many uses. For example, they're often used as sampling pumps for corrosive or toxic liquids. Since the liquid is inside the tubing, it doesn't come in contact with the pump's components.